Hello everyone and welcome to this webinar. This is Kevin Jones talking on behalf of PCI Geomatics. Welcome to the webinar on deriving mining and construction information from geospatial imagery with Geomatica and ArcGIS. The webinar today is being presented as part of an overall series of webinars that we've been hosting, and really the focus of these themed webinars is to hopefully convey that imagery is definitely containing a lot of information besides sort of using it as a backdrop. And so what we want to get across in these webinars is how easy it is to work with imagery and derive information that can be used for day-to-day business decisions. In this case, for mining and construction industry, we have a series of other webinars that we are doing as part of this. So just before we get started really into the actual content, I want to quickly mention a few things to be aware of. If you are in the webinar right now and you'll notice that your line is currently muted. That's automatic. The system mutes the line so that there's no feedback coming in from noisy rooms and that kind of thing. We can unmute your line. We probably will do that during the interactive question and answer period towards the end of the webinar. Don't wait until the end. If you have any questions or if you have a comment or something that you'd like to seek clarification on throughout the webinar, please raise your hand or type the question into the question panel, and we do have people monitoring the webinar throughout the session. There's myself and also someone else on the team who's taking care of that. So we will try to answer your questions and also bring it up in the live Q&A session. So today the presenters are myself on the right, Director of Marketing here at PCI, and your host, and a little bit of an introduction which I'll be giving. And Sean Malamed, who I've nicknamed our technical guru. He really knows his stuff when it comes to PCI's technology from top to bottom. So Sean's actual title is Pre-Sales Application Specialist, but if he's essentially our go-to guy for demonstrating the capability of the software. So before we get into it, I'd like to just quickly get a sense of what is out there in terms of, or those of you who are out there, what type of image processing software do you currently use? The reason we're asking this is to try to get a sense of, maybe there's some new people who have never used Geomatica before. Maybe you're thinking of complementing your tool sets. Maybe you only use ArcGIS and you don't really have a dedicated image processing software package that you use. But the intent of the session here is to hopefully give you a sense of how easy it is to work with Geomatica, and in particular for deriving information for mining and construction applications. So I'll just leave that open for a couple more seconds. It looks like just about half have voted so far. Just a few more seconds there. So it looks like there's a lot of people who are using Geomatica, which is great. A few of you are using URDAS and Envy. And there's a significant number of people who are doing image processing in ArcGIS as well. So that's really interesting. We will be showing how both software packages can be used together, specifically for this application, but also in terms of building workflows and scripting out different solutions. The first part of it is just to give you a sense of all of the other resources that we are making available as part of this webinar series. We have a series of webinars on the topic of getting more from imagery in specific application areas. We'll do a little bit of a background on mining and construction and talk about a few PCI customers who use our technology and have a lot of experience in this field, deriving information from imagery. I'll give a really quick introduction to digital elevation model extraction. Nothing too detailed, but just to give you a sense of what is capable. And then we'll have Sean take over and give a live demonstration. He'll be looking at Geomatica and ArcGIS, and he'll be working with stereo data to generate information that could be used operationally, things like volumetric calculations and identification of stockpiles and that kind of thing. And then we'll close off with just a quick look at the partnership with PCI and Esri, and do stick around till the end because we have an exciting offer that is available right now through PCI and Esri for a combined package software and also imagery. So stick around till the end and we'll go through that really quickly. So just quickly looking at some of these different application areas. The first webinar that we're doing today is focused on mining and construction. Here we have an example of the use of imagery to derive information that can be brought to bear for really powerful decision making. What you're seeing here in the middle of the screen is a color-coded map where we have actually extracted the digital surface model or the surface features on top of the terrain. In this case, these stockpiles. You can see the stockpiles here in the roadside imagery that was taken next to this building. And we're able to identify those stockpiles and measure the volumetric information that is contained in them. So, you know, although imagery sometimes is just used as a backdrop, through some simple processing in our software, we can extract elevation models, which Sean will be explaining and showing to you, and also using ArcGIS, we can calculate volumetric information and quantify the sizes of the stockpiles, which can really be used for operational decision making. Another webinar which we have coming up in a few next week, actually, on September 17th, is we're going to be looking at using black bridge imagery, so rapid eye imagery, which has this unique red edge band, which is quite sensitive to vegetation health. And we'll be showing you how we can very quickly derive vegetation indices. We have a few maps here showing on the screen where we've taken the rapid eye imagery and calculated vegetation indices, and then we'll produce some maps that can be disseminated out to growers out in the field or agronomists maybe who are looking at using this information to make critical decisions about the size, the nitrogen applications or the pesticide applications and so on. So then the other webinar which we have coming up, I'll just quickly go to that next slide here. We have a really exciting webinar where we'll be featuring the use of our technology as well as City Engine. For those of you who are unfamiliar with City Engine, is a tool that is made available through Esri, and we'll be using the digital surface models that we can extract from the stereo imagery. We will then be having actually a live presentation from Jeff Taylor, who is from Esri. He's one of the lead people working on City Engine, and Jeff's going to come in and give a demonstration of how they can use our DSMs with building outlines and through a set of automatic rules build out 3D features. So for rough level of detail, it's quite a powerful and automated method for doing that. And if there is a requirement or if there's a specific set of maybe iconic buildings or larger buildings, things that need to be modeled more accurately with superstructure and to be photogrammetrically accurate, we're going to be showing a tool that's part of the overall suite of offerings that we have, which is known as 3D Feature Extract, which allows you to model in 3D without the use of any 3D stereo equipment, glasses, or anything like that. It's basically a desktop application that uses the stereo data to allow you to build a geometry of the different buildings and then texturize those geometries. So quite an exciting webinar coming up there. And the final webinar in our series is on working with disasters. Here we have some mapping products that were generated from multi-temporal radar imagery, which was provided through our other partner, McDonald Detweiler. And RadarSat-2 imagery is what was collected in this case. We have some dry imagery and some flooded imagery, and we'll be going through an operational scenario, how to derive this information, and also we'll be focusing on the automation of producing this information through the power of Python scripting, which is what we have available as part of the Geomatica 2014 software launch. So getting into the meat of the topic for today, the mining and construction. So prior to this this webinar today, we did spend some time with some of our valued customers. One of which is shown here on screen, John Fairs, who's been working in the environmental engineering field for quite some time. He has a background in GIS, but he's very experienced in using remote sensing imagery and also GIS technology for operational applications in the mining and construction industry. And John said something in our conversation which we thought was really interesting, and he said that a DEM, or digital elevation model, is key to everything. And so at Dillon Consulting, which is where John is currently working, they have used the DEMs to measure productivity of various pits and quarries, and look at volumetrics on an operational basis. They've found benefits in terms of minimizing health and safety considerations by keeping staff away from dangerous locations, or minimizing the amount of staff that they have, surveying staff, in dangerous locations. And so really the power of imagery and the information that could be derived from stereo imagery in terms of DEMs is definitely something that is operationally used by Dillon Consulting on a very regular basis. The next customer we spoke to is Yannick Lantier, who is with WISA Environmental. This is a hydrologic environmental engineering company located here in Canada, and they have a really strong requirement on behalf of their customers. They have a lot of customers that that have quarries and pits, and those customers, they want timely, they want frequent collections, and they want derived information that is very accurate. And so at WISA, they have been using aerial imagery and also UAVs and sensors on board of UAVs to properly measure and measure very frequently the pits and quarries and the various stockpiles. They've actually done some research and found that as compared to ground surveying, they're typically within 2% in terms of their calculations of volumetrics of the different stockpiles. So the technology is definitely there, where the resolution is high enough, the elevation models that can be extracted, or the digital surface models that can be extracted, is very, very high resolution, and just the convenience of being able to measure that on a regular basis is definitely something that is helping their customers save time and money. In certain cases, their customers have to pay a percentage back to the government because they're essentially extracting a resource from the province or from the municipality, and so measuring exactly and reconciling exactly what they've extracted boils down to how much money they have to pay back as per their allocation of that resource. So it's critical for them to reconcile and measure precisely what they have extracted, and they're doing that operationally with aerial imagery. So just looking really quickly at the data requirements for deriving digital elevation models, here we have a couple of different scenarios. Typically for DEMs of high resolution, we need obviously some high resolution imagery. We have on the top here some commercial cameras. These are UltraCam and DMC cameras that are producing very high resolution imagery. the requirements for our software is that we need to have interior and exterior orientation information. We need that to be derived from the aero triangulation. We need the raw TIFF imagery, and from that we can do the whole workflow from importing the imagery, generating the DSM, filtering the DSM to DTM, and then producing orthorectified imagery, and also mosaics from that. Same holds true for satellite imagery. Stereo collects are possible with satellite imagery and are very common now with WorldView, GeoEye, Pleiades. These are all the different sensors that do collect stereo imagery, and Sean will actually be showing one of those. Concept is pretty straightforward. The viewing geometry changes as the plane or the sensor moves in space, but there's a strong amount of overlap. In this case, it looks like about 80 to 90% overlap over the same location. So the overlap portion has what's known as parallax, or different viewing angle that allows us to reconcile the location of that pixel in the third dimension in the z-axis. So using the stereo overlap portion, we can generate a DSM, and we do this with all of the overlapping images along the various flight lines, and then we can stitch all of those DSMs into one common DSM, which can be used for analysis, which is what we'll be showing today in the live demonstration. This is to give you an idea of the quality of the DSM that can be extracted from the imagery. In this case, we were working with 15 centimeter imagery, and the resolution of the digital surface model is roughly 3 times the resolution, the ground sample distance, so 45 centimeter DSM is what we can generate from 15 centimeter input imagery. And you can see here some large buildings. We also have some more residential housing over here, and we have some natural features as well that are visible within this DSM. Just some 3D renderings of the imagery on top of the DSM to give you a sense of what is possible. This is overlooking a waterfall in Quebec City here in Canada, and also we have just a different view here a little bit further to the east, looking towards the west, where we have some natural cliff and also some larger homes that are visible. So you can see some level of detail over in terms of the roof structure and the chimneys and this kind of thing on the data sets. So these are just pretty pictures, but this information can be extracted, and we can monitor the elevation information over time, which is what we'll be showing in the live demonstration. So just before we go to that, just before I pass over to Sean, I'm going to do one more poll. And I just want to get a sense of how often people are using imagery. You know, the reason we're doing this is to obviously get a sense of how familiar you are with imagery, whether you're working with it on a daily basis or a weekly basis. Maybe you're not directly responsible for working with the imagery. Really, the intent of this webinar is to give you a sense of how easy it is to work with imagery, in particular stereo imagery, and derive useful information. So looks like we have a large majority of people who work with imagery on a very regular basis. 62% so far are saying daily, so that's great. So it looks like a lot of people are familiar with it. Hopefully stereo imagery is something new maybe, and you're looking to see how easy it's going to be to extract elevation information and work with it, which is what Sean's is going to be doing next. So with that, I will pass over to Sean, who will give a demonstration here probably for the next 25 minutes or so, and then we'll come back to me.
All right, well, thank you very much, Kevin. That was a wonderful introduction into our suite of software and then how we can actually be quite useful for image processing within DEMs and for extracting DEMs and working within the mining application. So within this context, I'm going to be showing a variety of different hands-on demonstrations. Oh, we have a bit of feedback. So the first one that I would like to show is basically, or we're going to go through a variety of them, sorry. And the first one that I'm going to show is just in general how to extract a digital surface model or a digital elevation model from Geomatica. And this is using our OrthoEngine product with satellite stereo pairs. Now a similar concept can be applied with aerial, so I'm going to work with satellite in this case. After which I'm going to show you some of the different capabilities and different applications that you can use these extracted DEMs in terms of mining applications. So we're going to first focus on environmental stewardship, so looking at compliance and compliance reporting. We're then going to look at manually measuring volumes of pits and stockpiles. And then we're going to look at automatic productivity measurements, basically a automated workflow that identifies new stockpiles and measures the volume of those stockpiles. So the first thing we are going to look at, though, is just in general extracting the DSM with OrthoEngine. So as Kevin already mentioned, we got a wonderful quote, and in the mining world, when you're working on surveying, basically it's quite well known that the DEM is key to everything. It can be used to unlock a lot of information. For example, how much material has been moved from one place to another. Where have we actually been working? Where have things changed? So on and so forth. So we need to be able to first extract this information, which Geomatica is great for, before we can really begin to actually derive any information or useful information of our mining site. So a DEM is really just remotely surveyed elevation data that is used as the basis for analysis for deriving information. Now with OrthoEngine, OrthoEngine is going to be basically the tool that I'm going to show you here. And what we're going to do is we're going to just work with a simple project where we go to extract the digital elevation model from two stereo pairs. So I've already set up this project, and it's in, as I've already mentioned, it is in OrthoEngine. And I just want to quickly go through OrthoEngine in general. So OrthoEngine is a photogrammetric software application where it works on a top-down workflow concept. So you finish the processing steps for example, setting up your project, then you go down to inputting your data. Once that's done, you go down to the next step. You know, these are some optional processes here. And then you can go down to the next step until you get to the final product that you're looking for. So in our case, we worked with an optical satellite model, and we're using the rational function, so the RPC segment that's provided with that satellite image. We then set up our projection information and our output pixel spacing, so the resolution of our output image. Then we input the two DEMs. So here we have, the two stereo images. So here we have our right and our left looking stereo images. They've already been added, and they have a significant amount of overlap. Then we have our GCP and tie point collection panel. So in this particular case, and with satellite imagery, it's usually a good idea to collect at minimum tie points, but also some stereo GCPs. So in this example, we actually already did collect GCPs. And if we just open up this panel here, we can take a look at the table of our GCPs, as well as the distribution of our GCPs. So we can see we just have two, and that's really all we need, and they're stereo GCPs, meaning that they're used in both images. We have a very low RMS, which means we have a good model. And we can now go on to actually extracting the digital elevation model. So you would probably need to collect your GCPs. However, I would, in this case, we're just going to bypass that because the focus here is getting the DEM and then working with that DEM. So at this point, I would go right down from the GCP tie point collection, and I'm going to go right down to the DEM from stereo. Now, the first thing you would need to do is to generate your epipolar images. Now, we already have these generated because it takes about 5 minutes to generate, and I didn't want to spend 5 minutes watching a progress bar, so we pre-computed this. But it's very simple. You would just choose something like maximum overlap, and then just add the pairs to the table, and then click Generate Pairs, and that's all you need to do. The next area would be, after we have our epipolar images, is to actually extract the geocoded DEMs. So I can select the stereo pair that's online for this project, and I can go to geocoded DEM. I'm going to go to Create Geocoded DEM, and then I'm going to choose an output file name, and I'm just going to call it DEM_mine. Very generic. And I can set this resolution to anything I want. So I could set it to 1, which is probably the higher resolution that you would want for this. However, in this case, because this is just simply an example, I'm going to set the resolution to 10 so that it generates faster. We have a pre-computed DEM that we're actually going to work with, but in this case it's just to show you the steps in order to extract the digital elevation model. So at this point I can simply click Extract. I can actually click the button, and now it's going to go into the process of extracting our digital elevation model and then putting it into our final output folder. So this does take a few moments, but as you'll be able to see, it is quite quick, and we do have one of the fastest processing algorithms for DEM extraction on the market. And if we did have multiple images in this table, it would also have the capability of mosaicing those DEMs together, so you get a single DEM for your entire project area. So some very nice automated capabilities within OrthoEngine. Okay, so we're just going to let this finish processing. Actually, and rather than letting that continue or finish processing, let's just continue on to the full resolution. So what this is going to generate is basically a lower resolution version of this DEM that I've already previously computed. Oops. So let's just take a look at this DEM with a little bit better of an enhancement. So we can see that there's a lot of information in here, but we now need to extract this information, and there's many ways that we can do that. However, before we extract the information, we want to make sure that it's accurate. So what's also quite nice with Geomatica is not only do we provide you with the tools to extract the digital elevation model, we also provide you with tools to manually edit and perform accuracy assessments. So the way that an accuracy assessment is performed is that we can draw a one-to-one window over an area in our DEM. It's going to automatically orthorectify all the different images that intersect that region. And then based on the different viewing angles, we should get a final image, and we can flicker back and forth between the two. And then what we should see is that if the elevation is accurate, surface features such as the grass here, the roadway, pathway, whatever it may be, and as we can see the DEM completed processing, they should be stable, whereas buildings and trees are going to move back and forth. So let's just lower that. So what we can do now is we can go to our area here, go to DEM editing, and we can draw a one-to-one window. And it's going to orthorectify the two different viewing angles, or the two images based on the different viewing angles. We can then toggle back and forth. What we should see is that it should be quite relatively stable. And then we can identify where we have errors or where it's quite accurate. We can even use this to measure the vertical accuracy, which can be all very important in your report. So just to recap, we have the tools necessary to extract the digital elevation models in a very high-speed automated process, and we also have the tools to perform any necessary manual edits, as well as to perform the accuracy assessment without the use of 3D stereoscopic software. Okay, so let's just return back to PowerPoint for a little bit. So we're now going to jump forward and we're going to look at some concepts of environmental stewardship. Well, environmental stewardship, also compliance reporting. Now this is basically the concept that we need to be good stewards of the world when we're making changes to it. And in many regions now, it's by law that mining organizations need to adhere to their plans that were approved for the area, and they need to provide evidence that they are actually performing the work as described in the plans, in the design. So in order to do that, they've actually there's a lot of initial overhead in terms of planning to make sure that the landscape is altered, and or when the landscape is altered, that it's as minimal of an effect as possible. And some of the ways that we are able to provide this types of compliance reporting is through visualizations. It's one of the most common ways. Is we can provide digital elevation models and compare it to the initial plans to see, just to visually see how things look and how things have differed, as you can see here. We also have 3D fly-through capabilities. So we can actually render the digital elevation model in 3D space, drape an image over it, and then fly through it, and then we can compare that with artist renderings of the area of how it should be affected to make sure that it is in fact being altered the way that it's expected to be altered. So all this capability also exists within Geomatica. So I've already demonstrated to you. I'm just going to load the DEM here. Okay. So I've already demonstrated to you here that we can actually visualize it from a top view perspective. So we can see that. But what we can also do is we can click on this button right here, the Open Fly window. And this is going to automatically render our 3D model of the area. And then we can fly through this area to see how we might have affected it. And we can create videos of this and store these videos in order to present them to councils or individuals of interest, different stakeholders that might be interested in the development of the mine. So those are just some very quick visualizations capabilities. And of course we can also get the quick ortho of an area. So it's just a relatively large area. And then we can include this kind of information into the report so people can see how the land is being altered. So that's very important, is just the general visualization of the area in terms of compliance reporting. So we can see here. Okay. So now we're going to go back, and another key area it's important to consider is empirical comparisons. So what this is that when most mines are approved, or the design of a mine is approved, or the plans, they're often provided with 3D data sets such as contours, point clouds, rasters, tin models, etc., CAD designs, so on and so forth. So we can compare the plans based on the 3D data sets from the plans to the survey DEMs to identify areas where the work is deviated from the actual plan. So we see here an example where we might have a plan. Now obviously this is not a representation of a 3D data set, but let's just pretend for a second that that is. So it's the initial design, and then we can see how our actual work has progressed. And then we can perform empirical analysis on the area very quickly using Geomatica as well as ArcGIS in terms of identifying if there's a large difference between the actual, say, key elevation points and our actual digital elevation model. So that's just a quick note on compliance, on compliancy. So, another very important area to mining organizations is the volume calculation of stockpiles and pits. So I'm going to show you when we have a single DEM, so we don't have multiple DEMs to work from. I'm going to show you a manual approach for calculating the volumes of stockpiles and different pits. Okay, so calculating volumes of stockpiles, basically generic volume calculation algorithms, so the ones that you will find in most remote sensing and GIS software packages. The generic ones, they rely on the user providing a base elevation in which to calculate the volume from. However, the problem with this is that the Earth is very rarely perfectly flat. So stockpiles, as you can see in this graphic here, can often be on a slope. Now, depending on the size of the stockpile, that can be a fairly significant amount of difference that you can be calculating, or error that you can be introducing. And because stockpiles often equate to the amount of productivity, therefore there's dollars directly attached to it, we want to get as precise of a measurement as possible. So what we propose is a different approach, and it's using Geomatica's live DEM editing tools, so some phenomenal tools that I'll show you in a moment, to interpolate the surface based on the edges of the stockpile in order to more accurately calculate the volume of the area as opposed to working from a flat region. So here we're going to use, in this stockpile calculation, volume calculation, we're going to manually draw a perimeter around an area that we're going to pretend is a stockpile. Now we know it's not, technically it's not, but it's just to show the concept. And we're going to interpolate that surface. We're going to calculate a difference image, and then we can perform our volume calculation. We can do that in ArcGIS. So most of it will be done in Geomatica, and then we'll do the final volume calculation in ArcGIS. So let's get to that. Just going to make a copy of this one. Okay, so I'm going to render this, and just for our viewing pleasure, I'm going to load it as a pseudo-color DEM, or Hillshade DEM. And I'm now just going to create a empty vector, and I'm going to just manually digitize, not overly careful, just manually digitize around the stockpile. Okay, so it's coarsely drawn. So now with this tool I can go to Fill from Edges, and then I can just simply go Apply. It's going to interpolate, so it's going to remove that surface feature, and now it's going to give me a new DEM so that I can actually have an interpolated surface. Now if we click on different areas of it, you can see the elevation here. So we can see it goes as high as 737.55 in this corner, and then way down to 698. So we can see that we have almost a 40-meter difference in the area. Now this is obviously a huge region, and a stockpile will likely not be this large. However, this just goes to show that you can introduce error when you're just using a flat plane as the base. So now we can use this as our primary DEM. So we're just going to save it. This is going to be our example. So I'm just going to save the edit polygons. And I'm going to bring in the copy that I made. So this is the original one. So I'm just going to leave the editing mode. And we're going to go back here and we're just going to take a look at our DEM. So if we apply an enhancement to this one, we can see that we have contours here, elevation there. And if we go to our other one, we zoom in, apply it, we can see that it's flat. So we're just going to do a comparison between these two. Okay? So now I can go to Analysis, Change Detection. I'm going to choose my, as my working raster, the one with information above. I'm going to make this, choose the DEM. And then the second one is going to be my edited one, the one where I removed the stockpile and interpolated. I'm also going to make sure I choose the DEM. I'm going to subtract the two, creating a difference image. And I'm going to load it as a pseudo color. And I can quickly run. Okay, so now that it's completed running, we just need to update the pseudo color table. So we're going to choose a stepped ramp, and we can see our difference image here. So these are all the differences. So basically, you can actually think of this difference image as each pixel is basically, it shows the meter difference between the one DEM and the edited one where we interpolated the surface. So if we actually calculate the sum of this polygon, of all the different differences in this polygon, we can then use that to extract the volume. So it'd be like the integral volume of this feature. And then if we do, now this resolution happens to be 1 meter, so just the sum of all of this difference will actually equal the volume in meters cubed. However, if the resolution is different, we need to multiply the sum by the square of the resolution of our pixels in order to extract the actual in order to actually extract the volume in meters cubed. Okay, so now that we have this product, I'm just going to save this layer as a shapefile. I'm going to go to our analysis side now. We'll call this stockpile. Oops, I think I meant to save that as a shapefile. So just save that as a ArcGIS shapefile. Okay, save there. And we're going to save this layer also to our analysis. And we can just make this the diff 11, and we'll make it a TIFF, just for fun. Okay, we'll save that. So we can now go into ArcGIS. Okay, we're going to load our stockpile shapefile, and we're going to load our difference elevation. And we don't really need to build pyramids, but I'm going to. So we can see here our difference elevation. So now what we're going to do is we're going to calculate the sum of the differences inside this polygon. So I can go to System Tools, and go to Spatial Analyst Tools, Zonal, and I'm going to do zonal statistics. I'm going to choose my input, stockpile, so it's going to define the extents in which we're going to calculate the sum for. I'm going to choose my difference image, and then the statistics that we want is obviously sum. So I can then go OK, generates it very quickly, And then if what we actually get is an output raster where we have a single value for it. So, and then at this point, so this is the value that we have is actually the sum. So this is actually the volume. So as we can see, it's a huge value because it's a very large area. If we actually go to the properties for it, you can see that it's just an absolutely huge value, where it's over 62 million cubic meters. And then the last thing we would want to do is we can use either ArcGIS's or Geomatica's tools to then redigitize this into a polygon and store that sum value or the volume value as an attribute. And those tools are quite easy. You can either use ArcMap or Geomatica for doing that kind of application. So we're just going to skip that for now. And what we're going to do now is we're going to go on to the next stage. So the next one is also for calculating pits. Now we're not going to actually do this in a demonstration because we don't have the time for it. But basically we can use different methods for actually, because oftentimes with pits we just want to measure from a certain elevation. So what we can actually do with that is we can either go directly into the generic volume tools, or we can generate contours automatically and then just select one of the contours. So as we did here, this was a contour that was generated, it was selected, and then we just calculated the volume for the shape, for the area underneath that shape. Okay. So the final one, which is probably the most exciting one, the one that I really wanted to get to, is the one that involves automatic scripting. So Geomatica 2014, the new version of Geomatica, now includes a Python API. Now I hope you're as excited as I am about this, because this allows us to now create workflows within Geomatica that can seamlessly go into other software applications, such as using ArcGIS's ArcPy library. So now we can seamlessly go between some of our amazing image processing functions and then go into some of ArcGIS's wonderful GIS functions and algorithms. So we can take advantage of the best of both worlds, as well as other third-party open source software code, so on and so forth. So in this particular example, we have a problem. The problem is that we have a developer who wishes to acquire volumetric measurements of new and removed stockpiles, basically wants to assess what has changed on the site on a monthly basis in order to analyze productivity. So the solution is for them to acquire stereo aerial imagery, so to do flights once a month of the site, and then to have a script like the one that I'm going to present here to automatically extract and compare the changes in the DEMs. So what we have is we have the before DEM and the after DEM. And it's going to generate both of them, and it's going to perform a change detection between the two, automatically identify new stockpiles in our example, and it could also do find stockpiles that have been removed, but we're not doing that one in this one. And then it's going to automatically calculate the volume. And it's actually going to use a lot of the same functions that I showed you in the hands-on demonstration just a moment ago, except all this is going to be scripted. So let's get, let me just start the script. So I have a script here which basically takes advantage of both, as you can see, PCI as well as ArcPy functions. And it goes through a variety of different workflows. So I'm just going to, and if we wanted to be really creative, we could even create a GUI interface in order to launch the script. So I'm just going to call my Python the ArcGIS. The 64-bit is required because Geomatica is 64-bit. And so we're using the ArcGIS 64-bit background processes. I'm just going to drag and drop my script into this command console window and start it. So the first thing it asks me for is it wants to know the folder of all my input imagery that's going to be used to build the first DSM. So it's also going to extract the DSMs automatically. So here, my test one is the one that we're comparing, that we want to see the results from. So it's the 2011. And now it wants my reference one. So it's just, once again, it's just the images that are going to be used to build my reference DSM that we are going to compare with. Afterwards, it wants the mask of the construction site. So it wants to know where we should be performing the analysis under. So it's an inclusion mask, meaning we're going to omit all the pixels that are not within that mask. And then finally, it wants an output directory in order to store the results. So I'm just going to copy and paste that, and I'm just going to have it create a new directory. We'll call it volumetric analysis mining. Okay, we launch it. It creates the output folder, creates all the working folder necessary, so it begins to extract the test epipolar images right now. And then once that's complete, it's going to extract the DEM, and then go on and so forth. So let's just take a look at our PowerPoint slide to see exactly what the script is going to be doing. So as mentioned, the first thing the script does is it ingests the data sets, the actual raw images from our aerial camera. So it does the one for the 2009 and the 2011. Now let's just pretend that they're a month apart. And some of the key functions in this one, just in case you want to try to build this workflow yourself, because remember there's a recording of this video. So we're using the link function, the crproj function, cam import, and EO import in Geomatica. Afterwards, we actually extract the DEMs or the DSMs for both of these features or both of these areas, or rather data sets. So as you can see here, we get the DEM. Here's our construction site. So we get the area in 2009, and then we get the area in 2011. They look quite different. So in ours, we just want to find the new stockpiles that didn't exist in 2009 but do exist now in 2011. So the key functions that we use in this step in our script is the epipolar2 and autodem2, and these are both Geomatica functions. Afterwards, we then want to calculate the difference image of these. So we take the DSM from 2011, subtract it from 2009, and we identify where we have a positive difference. So here we can find out, and this is what I'm saying, is that we can actually use this difference image to identify where we have stockpiles that have been removed. So as you can see here, the green, and then where we have new stockpiles, which is the blue and the purple. The key function there was a function in Geomatica called chdet-op. It stands for Change Detection Optical. Then afterwards, we want the script to automatically extract stockpiles. So as you can see here, we're extracting them as polygons, as individual entities. And therefore we would be able to perform volumetric analysis on these individual polygons. The key function we use there is expolras, which stands for extract polygons from rasters, and this is also a Geomatica function. And then finally, it switches over to the ArcGIS workflow, and where we're actually calculating the volume. So we just use this simple calculation here, where we get the sum of the changes of the heights of each pixels. We multiply that by the resolution, the XY resolution of the pixel squared. Okay, and then as an output, that provides us with basically a polygon with an attribute field, now with a volume attribute field. The key functions that we used there was the zonal statistics, ArcPy, which is a spatial analyst, the raster algebra, ArcPy, which is also spatial analyst, and then ras2poly, which basically converts the rasters information from the zonal statistics to a polygons again, and then stores the value in the attributes table. And then we finally map it into ArcGIS. So that is the workflow that this script is performing. Let's just see where it is. So it looks like it's generating the DEM right now for the for the test image. Yep. So it's for the reference one. So it's just generating that DSM. It should be finish that DSM momentarily. At which point the final processes or the final analysis will be done very quickly. The most time-consuming process in this step is, in fact, the DEM extraction. So we'll just let this thing finish. It will not take too much longer. Oh, there we go. Looks like it's finishing up. And then, as mentioned, the final few processes will be very quick. So it's just building some overviews for the DEM to work from. And now it's going through the final sets of processes, doing the analysis, and it's done. So it took 297 seconds to complete that workflow. And what we get is basically, if we go to our output folder, we get this MXD file that was created. And has these polygons, and if we go to the attributes table, we can see, for example, the selected polygon has a volume of 5,154 cubic meters, and then so on and so forth. So we can identify different polygons. So we can go to another one, for example, this big one here. So we have 576 cubic meters, so on and so forth. Okay, so that's pretty much the demonstration portion of this webinar. I hope you found it educational. I hope you found it entertaining. And at this point, I'm going to pass the handle back over to Kevin Jones. Take it away, Kevin.
All right, thank you so much, Sean, for that demonstration. I'm just going to mute your line there for a second. And just as promised, the last few slides here before we go to the Q&A. So the relationship between Esri and PCI, the reason we're showing all this great technology and how it can work together is that PCI does have a really good relationship with Esri for a number of years now, going back to 2009. We've been a gold business partner for several years, and really when Esri had one of its biggest challenges that it was facing in terms of imagery, they turned to us. They needed to pan-sharpen, orthorectify, and mosaic 50 million square kilometers of GeoI imagery for publishing to the ArcGIS online platform. And they actually used our technology to do that. And so we have a good relationship with Esri, and along with them using our technology to perform their own processing of imagery, we've actually stood up some different programs together. This is one of the most recent programs that we had. We put together a Esri and PCI Geomatics Natural Resources Imagery Grant Program. The purpose of this was to provide software and imagery to organizations that really have an interest in doing more with imagery than using it as a backdrop, are really interested to further their knowledge on how to apply basics of image processing to get information from the imagery. And so about 22 different organizations were given free access to GIS software, so ArcGIS and Geomatica software for image processing. And they were also given some imagery from MDA, so radar-sat imagery, and also some rapid eye imagery from Blackbridge, in addition to some training to really look at what would be possible. So here we have a few different case studies where these are two of the grant recipients that I'm going to be showing here. The Metropolitan State University of Denver used stereo radar-sat imagery to create elevation model and also to look at slope and aspect information. They were looking at water that is contained in different glaciers and trying to interpret landforms from rapid eye imagery. So they were successful in their project, and that's a quick summary there with some maps that were made available through their project. Another example here is the Madison County Council of Governments in Indiana, and so the image that you're seeing here is the result of a multi-year change detection using RapidEye and Landsat, where land use classification was done to assess surface temperature change over the different years. In the case of Landsat, the thermal band was used, and also RapidEye was used to get a bit more detail in terms of the changes, the urbanization of this area. So this particular project, once again, was done with ArcGIS and Geomatica together. And so all this to basically let you know that you should find out if you're eligible to use these same tools to perform some work yourselves. We do have right now an offer available where we have both ArcGIS and Geomatica packaged together, and also you have the opportunity to get imagery from MDA and Blackbridge at a discounted price. And if you'd like to find out more about that, to see if you're eligible to purchase this suite of software and imagery, to do similar analysis that we did here for mining or for agriculture or any other application as part of our webinar series, do get in touch. You can contact us, marketing at PCI Geomatics. We'll make sure to pass on your information to the right person who can help you explain what the program is all about and what the offer is and how it can be leveraged. Just the one last little slide here, we are rolling out a series of webinars and also some live events. Here's just a quick rundown of some of the different events that we're going to be at, conferences in different parts of the world, and also some upcoming webinars which we've already mentioned. So with that, I think we'll go to the Q&A. So Sean, there were some questions that came in, and I'm just going to open up your line here so that you, so that you can help answer some of them. So one of the first questions that came in was actually relating to the number of GCPs. When you were collecting that stereo DEM from the GeoEye imagery, you only collected 2, but can you comment on the resolution that could be attained, or what improvements could be obtained if you did collect more GCPs?
Sure. So there's a common misconception that more GCPs equals a better model, and that's not always true. Now, that is often true, but not always. Basically, Digital Globe, actually, their satellite sensors, particularly GeoEye and WorldView, come with a very accurate RPC, rational polynomial coefficients, already. So really all we need to do is to collect 1 or 2 really good GCPs, very accurate GCPs, and use a zero-order polynomial, which is basically just a shift of the image, essentially, because there's very little distortion or radial distortion or so on. So therefore, 1 or 2 good GCPs could be actually sometimes more effective than collecting 20 GCPs on an image like that. Now, with that being said, it can also be counter if you are working with other sensors that do not have as accurate of an initial model, and therefore having 20 or more well-distributed GCPs may be necessary, particularly if you have to work with a polynomial order of 2, for example, where we're doing a lot of morphing of the image.
Perfect. There's a couple of follow-on questions relating to DSMs. One really good one is what it would be the vertical accuracy. For example, that DSM that you extracted from GeoEye, which I believe was 50 centimeter input imagery, what would be the vertical accuracy of that, Sean?
Well, the vertical accuracy depends on many, many factors. I mean, you can't really just throw a general statement out there and say that this is the vertical accuracy. It depends on the slope, how well we've did the correlation, a variety. Now, we have that accuracy assessment tool, which can be used to assess the vertical accuracy on different regions. Now, with a imagery like that, so we extracted a 1 meter DEM, I would expect that we should be able to get sub pixel accuracy with the correlation, therefore getting better than 1 meter vertical accuracy in terms of the actual height that we extract. So even though we're extracting a 1 meter DEM in terms of the XY pixel spacing, the actual vertical accuracy that can be expected can be lower than 1 meter, but it can also be a bit higher. But I would imagine it would, but it really depends. When we look at that image and we see how much it shifts, we can use that as an estimate to see how much we've actually, what our vertical accuracy actually is.
Okay. There's another good question here about a relatively new sensor which actually collects tri-stereo pairs, so Pleiades, which is a European satellite. Do you have any comments about how that helps using 3 as opposed to 2 satellite images?
Yeah, so I mean, if you have different viewing angles, you can extract more information. So it's basically where we get problems is we get when we do the correlation, we extract DEMs. We get what we call a score for that pixel, and that score is dependent on how well the correlation, how high the correlation is. The lower the score, the lower the correlation, and increases the likelihood of an error being made. So if we have different viewing angles, we can get a better chance of having an improved score for that pixel, meaning we get a better correlation because the viewing angle is more appropriate for it. So yes, working with tri-stereo with appropriate methods can create an improved output DEM, where we do less correlations or interpolations rather, and more direct extraction of information, which is the main reason why they provided the tri-stereo pair, is because it does produce a more accurate result.
Right. Excellent. Okay, great. Thanks. Another question here about the use of other types of data. You primarily focused on GeoEye. Can you talk a little bit about aerial imagery or maybe even UAV, sort of what is possible, what isn't possible at the moment?
Absolutely. So basically, we work a lot with aerial imagery as well. I've worked with DEMs around 30 centimeters, where the imagery that was used to extract those DEMs were 10 centimeters. And basically, so these very high resolution photos, ortho photos and DEMs that we're using can be quite nice to extract certain types of less complex buildings and surface features. However, using the methods that our software incorporates, which is a sparse matching method, it's not currently possible to get perfect, perfect buildings where they could basically be thrown into a 3D model and they will perfectly, they'll be as good as, say, the buildings you see in Google 3D. Now, with that being said, we do have a software such as our 3D feature extract, which there's a webinar coming up for it in the next couple weeks. And basically this software can then be used when you have certain buildings that you need to get the perfect edges and model it perfectly, this particular software can be used in that case.
Okay, great. Just putting up the information there on the webinar for that person that was asking about extracting buildings and so on. Just as a reminder, this is the type of detail that can be done, that can be extracted from the imagery. And do come back next week on September 18th. We'll be going through that in detail. Another question about the Python workflow, Sean. The final result that you had there was an MXD file, which was like a local project. But would there be a way to push that content out to people, either via email or via web services?
There's many different ways that we can disseminate the information. One way is just to create a simple map document. Another one would be, for example, to create a GeoPDF, which can definitely be done through scripting, and then of course we could push it out to the map as a WMS service. So absolutely, there's many different ways to disseminate the information.
Great, and I guess that's going to be the subject of the webinar that's coming up specifically on Python. That's going to be October 23rd, I think. So we'll be showing not only how to work with ArcGIS, which we've shown today, but we'll be showing some other possibilities of connecting Geomatica technology with pretty much with a real varied array of technology, whether it's web mapping or FTPing, or really there's a lot of possibilities. That's going to be the subject of the webinar on October 23rd. Okay, just trying to see if there's any, there's some people asking about the availability of the presentation. Yes, we will be making that available, of course. Question here about heavily wooded areas and steep slopes, slopes that are greater than 45%. How would you remove trees and get to the terrain model, and how can you comment on the workflow there and how you would go about doing that?
Yeah, well, we have specialized filters in our live DM editing tool that can be used to help remove the canopy and retain the slope. But in those particularly challenging areas where you have slopes such as greater than 45%, we can actually employ a method called using stabilizers. So if there's any areas where there's information between the trees, where we actually have a bit of an opening, we can apply a stabilizer there, and that will help to make sure that when we do remove the trees that we're not removing the natural terrain or as much of the natural terrain. Now, if we can't see anything on the ground, I mean, this is technically, this is photogrammetry, so we need to see information to make information of it. So if there's absolutely no information on the ground, of course that can be a challenging area to work on.
Okay, great. Well, that was quite a few questions, and I'm really happy to see that most people have stayed on right till the end. So with that, I think we'll close it here. We want to thank you once again for attending today's webinar. It's been a pleasure for us to provide this information to you. We're glad you came, and we hope to see you at some of the follow-on webinars. Be sure to tell your colleagues about all the great information that we're passing along here, and we'll talk to you very soon. Thanks for attending today. Thank you, Sean.
Everyone. Yeah, thank you.